Lecture 2.16, Energy and Momentum. Here's a summary of some of the results from the previous lecture. We found expression for relativistic momentum, which is just gamma times the classical momentum. Kinetic energy was gamma minus 1 times m naught c squared. Total energy, gamma mc squared. Rest energy, mc squared. And then the force was gamma cubed, mass times acceleration. We have a series of results that are brought straight over from classical physics and work for special relativity. So Newton's second law, definition of work kinetic energy theorem. These formulas all apply to both classical physics and relativity. Also, we are defining m as the rest mass. So if you see an expression with an m naught or just an m, they mean exactly the same thing. We're probably going to go back and forth between them. Okay, so one of the first results is going to be a homework problem. We want to find a relationship between energy and momentum. So you might remember that in classical physics, the kinetic energy is momentum squared over 2m. We want to find a similar kind of expression for relativity. So remember that momentum is gamma mu, energy is gamma mc squared, and so you're going to derive this expression here, that the energy squared is pc squared plus mc squared. So the way that you would approach this problem in the homework, to derive this relationship, you need to eliminate the velocity dependence between these two equations. So note, this final expression doesn't explicitly contain a velocity. So we've got to get rid of the u, and we've got to get rid of the gamma factor, which also depends on u. So one way of doing it is to square the momentum expression, plug in for gamma, and then solve for u squared in terms of momentum and mass. Right? So you can solve this expression for u squared in terms of momentum. Then you can take that value and plug it in for the u squared that appears in the gamma term inside the energy expression. And then you just do algebra. All right, so now we're going to see what you can do with this expression. So first of all, notice that in this equation, you can see that momentum times c, pc, has got to have units of energy. Since we like to express energy in electron volts, we'll express momentum in electron volts divided by the speed of light. So here's an example. Suppose you wanted to find the momentum of a proton with energy of 1.5 GeV. So you can use this expression. We know the energy, and we're trying to solve for the momentum. So move the rest energy squared to the other side of the equation, and then take the square root. So you get that momentum times the speed of light is this. And now you just plug it in. So we'll convert our energies into MeVs. So 1.5 GeV is 1500 MeVs. The rest energy of the proton is 938 MeV. Plug it in, you get 1770 MeVs for PC. So if you wanted, you could write that as 1.77 GeV, or if you just wanted to solve for a momentum by itself, it would be 1.77 GeV per c. So again, this is the notation that we like to use. Don't plug in for the speed of light. Always leave it in terms of electron volts just divided by c. What else can we learn from our energy-momentum relationship? One thing that falls out of it is properties of massless particles. So we're going to define a massless particle as just having, the mass equal to 0. So mc squared is just going to be 0. If we look at the energy-momentum relationship and plug in 0 for the mass, you get energy squared is pc squared. And so if you take the square root of both sides, you get energy is the momentum times the speed of light. Very simple relationship between the two. This has got an interesting conceptual implication here. It says that massless particles, like say a photon of light, can carry momentum, which is not what you'd expect from classical physics, right? In classical physics, the mass of a particle is mass times velocity. So if you had a particle with 0 mass, you would expect 0 momentum. But in relativity, things are not as you expect usually. So this is telling us that even a massless particle can somehow carry momentum. Another result is that we can show that massless particles must travel at the speed of light. You can't slow a massless particle down. You can't slow a photon down. So one way of showing this or motivating it is that if we accept this result that energy is equal to momentum times the speed of light, and we want the momentum, which is gamma mv, that's relativistic momentum, we want the momentum to be non-zero in the limit that the mass goes to 0. Okay, so we'll expand this out. So we'll write that the momentum is mass times velocity over the square root of 1 minus u squared over c squared. That's plugging in for the gamma factor. We're going to take the limit of this thing as mass goes to 0. So when that happens, the numerator will go to 0. But remember, we want this result, we want this limit to not be 0. So the only way that can happen is if the denominator is also equal to 0. If the denominator is 0, the only way that can happen is if the velocity equals the speed of light. So anyway, that's a bit of a roundabout way of getting there, but this is one demonstration showing that massless particles must travel at the speed of light. So here's a little summary of the properties of massless particles. So their mass is 0, energy is equal to momentum times the speed of light, and their velocity is the speed of light. A close cousin to massless particles are highly relativistic particles. So we're going to define a highly relativistic particle as one that has a total energy much, much greater than its rest energy. So when this limit applies, so if energy is much greater than if the energy is much greater than the rest energy, we can basically ignore the rest energy term compared to the energy here. So that goes away, and you get that the energy is approximately equal to pc. So remember this, if the energy equals a momentum times the speed of light, that's an exact relationship for massless particles. In highly relativistic particles, we get an approximate equality. When the energy is much greater than its rest energy, remember that the gamma factor is the total energy over its rest energy. So when E is much greater than E naught, this ratio is going to be much bigger than 1, and so therefore the gamma factor is also going to be much bigger than 1. Finally, remembering that the kinetic energy is the total energy minus the rest energy. When the rest energy is tiny compared to the total energy, you can just neglect it, and we'll see that the kinetic energy is approximately the total energy. So again, if you have a situation where there's a highly relativistic particle, these are things that are true about them. So again, energy much greater than the rest energy, energy is approximately equal to pc, kinetic energy approximately equal to total energy, and the gamma factor much greater than 1. We'll talk about collisions of particles next, and so it'll be helpful to think about conservation laws that come over from classical physics. So we've already seen that momentum is conserved in relativity if we define it relativistically. So the total momentum of a system before is equal to the total momentum after. as long as a system isn't being acted on by external forces. Same for energy. So energy is also conserved during collisions. So the total energy before and after will be the same. But that's assuming that we add in the rest mass into the calculation of the total energy. You can't just add up kinetic energies. You have to include the rest energy. However, mass is not conserved. So unlike in classical physics, mass is not conserved in relativity. So so we'll think about these conservation laws and apply them to the collision of two particles. Okay, final example in this lecture. Let's look at a collision between two particles. So here's an example of putting energy conservation into practice. So suppose you got two particles. They both have rest energy m. They are moving in equal to opposite direction. So when they collide, we're going to assume that they stick together and form a new particle of mass capital M. In classical physics, the mass of this particle would be just 2 little m. It would just be the sum of these masses. We're going to see that that's not true in relativity. So we're going to use energy conservation to calculate the total energy of the system before the collision and set it equal to the total energy after. So the total energy before the collision, we just add up the total energies of our two particles. So total energy is gamma mc squared. These are identical particles with the same velocities, so these two terms are the same. And the total energy of the particle after the collision, it's at rest. So it's just going to be its rest energy, which is just big mc squared. So why do we know that the final particle is at rest? Well, it's because the momentum of the system before the collision is equal to 0. By momentum conservation, the momentum after the collision is also going to be 0. Okay, so our expression for the total energy here is 2 gamma mc squared equals mc squared. Big M is equal to 2 gamma m. We canceled out the c's there. And that's it. So that's the total mass of the system. We see that the total mass of the system is not equal to 2m, as you'd expect in classical physics, but there's a gamma factor in there. So if we wanted to see what the change in the mass of the system is, well, we'll take the rest mass of the system after the collision and subtract the rest mass before the collision. The change in mass is going to be 2 times quantity gamma minus 1 times m. So we've seen that this is an example where mass is not conserved in a relativistic collision. So the mass of the system goes up as a result of the collision. So we can plug in some numbers. Let's suppose that our two particles are protons. Let's say they're going at 90% the speed of light. You can calculate the gamma factor. So the total mass of the system afterwards is going to be 2 gamma times the mass of the proton. Plug in that. So we get 2 times the gamma factor, 2.29, times the rest mass, 938 MeV per c squared. So you get 4,300 MeV per c squared. So notice that the kinetic energy of the particles before the collision, we'll say there's two particles, so it'll be 2 times k times gamma minus 1 mc squared. Plug in the gamma factor and the mass of the protons, you get that this is the kinetic energy of the particles before the collision. We see that if we take the rest masses of our two particles and add it to the kinetic energy, you get the rest mass of the particle after the collision. So this is a pretty remarkable result. We see that kinetic energy of the initial protons was converted into the mass of the final object. Right? This does not happen in classical physics.